Okay, we're going to now turn our attention to the histology of epithelial cells. And we'll use this as a way to sort of understand what the basic cell structure is for epithelium. And then later on, when we go through the different organ systems, we'll take a look more specifically at the different kinds of epithelia that are found in different organs. So what we want to accomplish for now is to describe the structure and function of transport across epithelial cells, because that is a major function of epithelial cells in many different organ types. We want to see what histologically the different epithelial subtypes look like, and then we want to take a look at some specific cell biology of the cytoskeletal elements that are found inside the cells. Cell adhesion molecules responsible for maintaining the integrity of cell attachment, cell junctions and what their role is, and then cell surface specializations that are going to be found to help epithelial cells do their specific jobs. So we'll first look at epithelium, then cytoskeleton, then cell adhesion molecules, then cell junctions, and then cell surface specializations. So epithelial cells, the one characteristic that we can certainly say about them is that they line surfaces. They line surfaces, and those surfaces may be external surfaces, like the surface of the skin, or they might be internal surfaces, like the surface lining a lumen, the lumen of, let's say, the esophagus, the lumen of the trachea. Okay, but they line surfaces. Often these epithelial cells are polarized, meaning that one side of the epithelial cell functions in a way different from the other side and has different modifications to accommodate those functions. Okay, when they are polarized, one side would be the side that we would call the apical surface, and that's typically the surface that's facing the surface, the region that's being lined, the lumen or the surface of the skin. And then the other surface would be called the basolateral surface. That's where the epithelial cell will be in contact with other cell types or other tissues. We're often going to see that there are going to be junctional complexes called tight junctions that will separate the two regions that have these two different functions. And we'll see what we mean by that in a few moments. And these tight junctions are going to be essential to maintain the integrity of the polarity and thereby maintain the integrity of the transport function. The role of many epithelial cells is, as I said, transport of substances from one side of the cell to the other side of the cell. So, for example, if you have an epithelium lining a kidney tubule, then the function of that epithelial cell may be to transport substances from the space containing urine to the tissue space. Okay, the transport of salts or sugars across that epithelium. If that's an epithelium lining, let's say, the GI tract, the small intestine, then that epithelium may be transporting nutrients, for example, out of the food that's in the lumen into the tissue and into the blood supply that's on the other side of the epithelial cell. Now, in order to get material from one side of an epithelial cell to the other side, there are really two basic mechanisms that can accomplish this. One mechanism is called transcellular pathway, in which the material is being moved through the epithelial cell. In other words, it enters on one side of the epithelial cell, goes through the epithelial cell, and comes out the other side of the epithelial cell. The other pathway is called the paracellular pathway, in which it doesn't go into the epithelial cell at all, but rather goes around the epithelial cell, passing between epithelial cells. When you have a paracellular pathway, that pathway needs to be regulated to regulate the passage between cells and to regulate the direction of passage between cells. And so we're going to see that we will have junctional complexes between those cells that maintain the integrity of those paracellular pathways to control the direction of transport. Okay? And this polarity that we talked about is, of course, essential in order to maintain the normal, proper functioning of the cell. If you disrupt the polarity, you're going to disrupt epithelial cell function, which can lead to disease. Okay, so for example, we have some epithelial cells in various locations where there is a function of the epithelial cell to transport chloride ions from one side to the other, from the basolateral surface to the luminal surface of the cell. So there is an active process for transporting chloride ions across the epithelial cell. Once we've transported chloride ions across by ionic forces, that will drive sodium across. So now we have sodium chloride moving across from one side of the epithelium to the other, and with the passage of sodium chloride, water will follow. So now we have established a mechanism for transporting water from one side, from the basolateral surface, into the luminal surface of the cell. Well, if we disrupt that process, if, for example, there's a defect in the channels through which the chloride ion passes, if you're not appropriately transporting the chloride and therefore not the sodium and therefore not the water, you're going to have a defect in water transport across the epithelium into the lumen. With decreased transport of water into the lumen, the mucus that's being secreted by mucus-secreting cells into that lumen, that mucus is going to have less water diluting it, and the mucus therefore will become much more viscous, a thickening of the mucus layer. And this, what we just described, is in essence what occurs in cystic fibrosis. So cystic fibrosis is a disease in which the primary defect is a defect in the chloride channels of epithelial cells lining surfaces of the GI tract, of the respiratory system, and so forth. Epithelial cells themselves, epithelial layers are avascular. You don't have blood vessels within epithelial layers, so you need to have blood vessels near epithelial layers in order to provide the oxygen and nutrients to the epithelium. So epithelial cells will always be alongside a connective tissue layer that will contain blood vessels. And those blood vessels are necessary for the support of the epithelium. Okay? And therefore, those epithelial cells are separating the blood vessels that are on one side, the connective tissue layer, from the lumen on the other side. So the epithelial cells have the ability to modify both of those compartments. In other words, the connective tissue compartment and the luminal compartment. And so you can transport material out of the lumen into the vasculature, or you can transport material out of the vasculature into the lumen. So depending upon the direction in which you're moving, you're going to modify both compartments by taking materials out of one compartment and moving them into the other compartment. Now, because epithelial cells are lining surfaces, and as such they're subject to damage from whatever they come into contact with, epithelial cells frequently have to be replaced as they get damaged and die off. So wherever you're going to have epithelial cells, you're going to have the ability to replenish those epithelial cells with stem cells. So we're always going to be looking to where are the mitotically active cells that are serving as the stem cells to actively replace the epithelial cells. You're always going to anticipate having turnover of epithelial cells. Okay, so let's look at the different kinds of epithelia that we have. Now, we've said that epithelia line surfaces. We're going to categorize these epithelia based upon what the epithelium looks like, based on two observable characteristics. One characteristic will be how many layers of epithelial cells are there? How many layers are there between the luminal surface and the connective tissue surface, or the basolateral surface? How many layers of epithelium are there between the basement membrane and the lumen? If there's only one layer of epithelial cells, then we would call it a simple epithelium. If it's more than one layer, then we would call it a stratified epithelium. So those are going to be the two basic kinds, either one layer of epithelium or multiple layers, simple or stratified. The other way of categorizing it is based upon the shape of the epithelial cell that's at the surface. And so we'll look at the cell that's at the surface and say, what shape is it, and give a name to that shape. And that will give us the other characteristics. So, for example, looking at this epithelium that we're looking at on this slide, here's the lumen, there's the basement membrane. We can see there's only one cell layer separating the basement membrane from the lumen, one cell layer. And so this would be a simple epithelium. And that cell that's at the surface is cuboidal in shape. Cuboidal in shape. It's about the same dimension in this direction as it is in that direction. So it's sort of cuboidal in shape. And so we combine those two characteristics and we say that this is a simple cuboidal epithelium. Simple cuboidal epithelium. And this happens to be an epithelium that's found in the renal tubules. Okay, it's also the epithelium that we found in certain glandular cells, simple cuboidal epithelium. Okay, so that's one kind of epithelium. Here we're seeing an epithelium. Again, there's the lumen. Here's the basement membrane. So between the lumen and the basement membrane, again, it's only one cell layer thick. Right? That's one cell. So again, it's a simple epithelium. But now the shape of that epithelial cell that's at the luminal surface is not cuboidal, but it's longer in this dimension than it is in that dimension. So we call it columnar. So we call this a simple columnar epithelium. One layer thick, and the cell shape is columnar, simple columnar epithelium. And that is an epithelial type that's found lining the small intestine. Much of the GI tract is lined by simple columnar epithelium. So that would be characteristic of the GI tract. Okay. Here we're looking at this epithelial surface here. There's a lumen. That happens to be the lumen of a glomerular Bowman's capsule. So this is in the kidney. Okay. So that's the lumen of what's called Bowman's capsule. Okay, in the kidney. So that's the luminal surface, and that cell separating the lumen from the basement membrane, it's only one cell layer thick, very thin. So it's a simple epithelium, and that cell is very flat, very, very flat. It's not cuboidal, it's not columnar, it's flat. The word for flat is squamous, so we call that a simple squamous epithelium. It's a very thin layer of epithelium. It's only one layer thick, and that single layer is a very thin cell. That's a simple squamous epithelium. And we would expect to see simple squamous epithelium, in other words, an extremely thin epithelium, in places where we want to see things moving across that epithelium pretty easily. So we're going to see that lining blood vessels, endothelial cells. Okay, we're going to see that on renal tubules, Bowman's capsule rather, in the kidney, where we're going to have material crossing from the blood system into the renal system. We're going to see that in the alveoli of the lungs, where we want to have gas crossing from the airway into the blood system. So where you want to have very simple, when we want to have stuff being able to get across that layer very easily, you want a very thin single layer of epithelium. So that's where you'll find simple squamous epithelium. Now, this is a variation of an epithelial type that has an interesting name. It's called pseudostratified columnar epithelium. Pseudostratified. So we know what stratified means. It means that it has more than one layer. And when we look at this, here's the basement membrane here. Here's the lumen here. And when you first look at this, if you take a quick look, it looks like there's 1, 2, 3, maybe 4 layers of cells, right? It looks like it's stratified. But if you look at it more carefully, you'll see that it really isn't. That all of these cells, each of these nuclei is in a different cell, and every one of those cells reaches the basement membrane. So this cell is reaching the basement membrane. This cell is reaching the basement membrane. This cell has a cytoplasmic process that reaches the basement membrane. This cell reaches the basement membrane. So all of the cells reach the basement membrane. So it's not really stratified. In that sense, it's simple because they're all attached to the basement membrane. But it looks stratified, so we use this term pseudo-stratified columnar epithelium. So we have these columnar cells. Some of them are very tall, so they go from the basement membrane all the way out to the lumen. Some of them are not as tall. Some of them are even shorter. Some of them are even shorter. So they have their nuclei in different positions, giving it this pseudo-stratified appearance. Pseudostratified columnar epithelium is an epithelium that we'll see in a good bit of the respiratory system. So this is actually from the trachea. Okay. Here's another specialized kind of epithelium with a specialized name, and it's called transitional epithelium. Transitional epithelium is going to be found in some of the organs of the urinary system, specifically the urinary bladder and the ureter. The reason it's called transitional is because the number of cell layers thick that this epithelium changes over time. It's not static, it transitions. So when we look at this, the basement membrane is down here. It looks like there's 1, 2, 3, 4, 5, 6, maybe 7 or 8 cell layers thick. Here we're looking at the wall of the bladder when the bladder is empty. Here's the lumen of the bladder, and it's empty in this image. If we were to fill the bladder and thereby stretch the wall, we would see that the epithelial cells would rearrange themselves and spread themselves out, so it may be only 2 layers or 3 layers thick. So it transitions between being 5 or 6 or 7 layers thick to being as few as 2 layers thick, depending upon the degree of stretch of the wall. Okay? And so we're going to see that lining the surfaces of organs that tend to stretch a lot, like the bladder and even the ureter. And the other thing that makes transitional epithelium particularly important as an epithelium type in these organs is that it is designed to not permit transport of material. Okay, it's pretty much impervious, and material does not transport. And that makes sense. You know, in the urinary system, after we've gone to all of the trouble to filter the blood and produce urine stuff that we want to get rid of, we certainly don't want it to be lying on an epithelium where that's going to get absorbed back into the bloodstream. So transitional epithelium is relatively impervious to material getting through it. And another kind of epithelium is called stratified squamous epithelium. So for right now, let's ignore this layer and look at this layer. This layer here, which is the cornified layer of this layer, these are actually dead cells. So we're not going to look at that for right now. Here's the surface of the epithelial cells. And these cells are flat. So it's a squamous epithelium because the cells at the surface are flat, but we see that they are sitting upon multiple other layers of cells. So this is a stratified squamous epithelium. Stratified squamous epithelium. There we see it go. Stratified squamous epithelium is going to be found on surfaces that are subject to abrasion. Stratified squamous epithelium is particularly good for resisting abrasion. So we're going to see it on surfaces where there's going to be abrasion. Surfaces like skin, surfaces like the esophagus with food moving down along the surface causing abrasion. So we're going to see stratified squamous epithelium lining surfaces that are subject to abrasion. Now, sometimes those surfaces, like skin, are also subject to desiccation, where you can lose water through the surface to the environment. And if it's a surface where you can lose water to the environment, in order to prevent or reduce the loss of water, we take the cells, remember we said epithelial cells die off. When these cells die off, we don't immediately get rid of them. We let them sort of stack up and cover that epithelium, forming a layer that sort of serves as a water barrier to prevent the loss of fluid. So this would be a keratinized, these dead cells now called keratin, it's a keratinized stratified squamous epithelium. So that would be on the surface of skin, where not only do we want to resist abrasion, but we want to resist desiccation. If we were looking at an internal surface, like the lining of the esophagus, where we are concerned about abrasion, but we're not concerned about desiccation, then you would not have a keratinized surface. You would have a non-keratinized stratified squamous epithelium. So you'd have these layers from here on down. These dead cells would not be there. They would be lost. Okay, and then one more cell type that we should look at. The last one that we're going to look at is called a stratified cuboidal epithelium. So here we see a lumen. That lumen is being lined by these cells that are cuboidal in shape, but we see that there's another layer behind them between the lumen and the basement membrane. So this is a stratified cuboidal epithelium. And stratified cuboidal epithelium is an epithelium that we tend to find in ducts, gland ducts. So it could be salivary glands, as this is. It could be mammary glands. It could be sebaceous glands. Okay, so it's the ducts of glands tend to have stratified cuboidal epithelium. Okay, when we get to histology of specific organs, when we get to those specific organs later on in our discussion, you'll want to pay attention to the functions of different organs within an organ system and think about what kind of an epithelium would be best suited to serve that function. Because if you correlate function with structure, if you say, well, here's a particular function I want to serve, like absorption, or here's a function I want to serve, like resistant to abrasion, and then say, well, what kind of epithelium would be best suited for that? That'll pretty well tell you the answer of what kind of epithelium you will find in that organ. So you really want to associate function with the structural histology that you're going to be looking at.